And what is going to happen to all of these samples? How is the classifier going to label them as? Well, if the threshold is greater than 0, all of these confidence values is greater than 0. And so we're going to classify them all as having a target. All of them will be classified as being targets. Okay, so let me go to the chat. I think there's some confusion about the position of the targets on this table. Okay, so let me rephrase it. So each row, let me maybe write it like this. These are samples. They're spatial samples in this case. Okay, so you can think of, I think this problem when I designed it, I was thinking about some Navy applications where they place landmines on the floor and then they take pictures, high spectral cameras, imagery from up top, and they want to detect where these are. Okay, and so these are spatial samples. So I have X1, X2, X3, X15. So there's 15 samples, and each sample is a hyperspectral imagery, right? So you can think of it as just an image that has some information, and then you feed it to a classifier, and the classifier will give us a confidence for or a probability for a target to be present in that image. And that's what this confidence value is. Right, so for sample X1, the classifier says there's 91% chance that there is a target, that there is a landmine in that image. Okay, X2, the algorithm detects 90% chance for the landmine to be present in that sample. Now the ground truth label is, we know whether or not there's a target at that location. Right? And so we know that for sample X1, indeed, there is a target. For sample X2, there is a target. That's why I mark it with a T. For sample X3, there is not a target. Right? And so we want to use this, the confidence values retrieved by the classifier and the ground truth labels to determine what is the value for our confidence that we should use to maximize the true positive rate and minimize the false positive rate? Hello, can you hear me? Okay, I'm not sure what happened. All of a sudden, the Zoom just shut down. So I'm going to go back. And let me know if you've missed something. What was the last thing that you hear me say?
You had just finished like answering the question. So
Okay.
I think we got all that.
Okay, thank you. Okay, let me switch back. I'm not sure what happened. I think it's still recording, yeah. Okay. And so we're looking for what is the threshold that we should use to then use this classifier on the field, right? And we want to choose the threshold that maximizes the true positive rate and minimizes the false positive rate. And so that's exactly what the ROC curve is going to give us, right? It's for each choice of the threshold, we're going to have a pair for true positive and false positive. And that's going to be a point in my curve. Okay, and so suppose that the thresholds is equal to 0. So that means if the confidence value is greater than 0, the threshold, then the classifier is going to classify that sample as having a target. Okay, and so that's the green column here. And so all the confidence values are greater than 0. And so all of them will be labeled as having a target. Okay, so now let's compute the true positive rate for threshold equal to 0. So we have the true positives, and how many do we have? So we're going to correctly classify 1, 2, 3, 4, and 5. Those are the true positives. And then TPR is true positives plus false negatives. But we don't have any false negatives, right? So no point was classified as negative, so that's 0. So TPR is equal to 1. So yay, we maximize TPR. So now let's see the FPR when threshold is equal to 0. And again, FPR is false positive divided by false positive plus true negative. So what is the false positive? We have 1. So everything that was classified as targets, but we don't have a target. Okay, so those are going to be 10 of them. Right? And the true negative, we have 0. Okay, so FPR is equal to 1. So that's a terrible value for FPR, right? But now in terms of our curve, that's going to fill in that point. It's going to be here, right? And now we're going to just build more points with different threshold values to build a curve. Okay, so now what I want to do is to try out different thresholds. Let's see. Okay, I think I'm just going to try here. So if the threshold is equal to, for example, 0.1. Okay, so what is the true positive rate for this? This table is a bit messy. Hopefully you can see it, that for a value of 0.1, we're here. We're going to miss this value, right? Because it's smaller than 0.1. So thank you, Andrew. That's exactly the answer. So the TPR, it's going to be 4. We're going to correctly classify 4 out of 5. And the false positive rate, it's going to be, well, this one is going to be correctly classified as a negative class. And these ones are going to be classified as having a target, right? And so we're going to have 9 out of 10. Does that make sense? And so that's another point in my ROC curve. So I have 9/10 and 4/5. So that's going to be somewhere around here. Okay. Now we're going to try a different thresholds. Say 0.4. What is the TPR? And so the threshold is greater or equal than 0.4. We're still going to miss this one down here, but this one, so we're here, the threshold is here, that one is going to be counted because the confidence is at 0.4. And so we still have 4 out of 5. Now for false positive rate, it's going to be a much smaller number. So we're going to have 1, 2, 3, 4 out of 10. Does that make sense? Okay. And so that's going to be another point. So somewhere around here, 4/10, and 4/5. So it's going to be here. Okay. So let's do 2 more. Let's do thresholds greater or equal to 0.8. What's the TPR? So now as we increase the thresholds, we're going to increase the false positive rate, right? Excuse me, the false negative rate, right? And so for this particular case, we're working at these thresholds. And so we have 2 out of 5. And for false positive rate, we're going to have just one such point that was incorrectly classified as true. So 1 out of 10. And so that point, it's going to be somewhere around here. Okay, and so let's do the last one when epsilon is, the threshold is greater or equal than 1. Then the true positive rate is going to be, it's going to be 0, right? There's no confident values larger than 1 or equal than 1. And the false positive rate is also going to be 0. Okay. And so we can build our ROC curve like this. So we have this point until we don't see a new observation, we hold it constant, okay, like this. Oops. Like that. Okay, and it's bounded at 1. Okay, and so the more points we have, the less edgy this curve is going to look like. Okay, so it's going to look a little more smooth. And so we see that this is certainly performing above, above the random, right? But it's still not perfect, right? Okay. Okay, so any questions about this? Okay, so let me switch to notes. Now, suppose that you're segmenting the data set into 3 classes. Okay, so you take the same pictures and you're trying to segment it into whether there's vegetation, man-made materials, or sand. And you wanted to evaluate your results. Would using a ROC curve be an appropriate method for evaluation? What do you think? So again, the ROC curve is binary, a binary measure, right? So it's measuring the performance of each class individually. So vegetation versus everything else, man-made materials versus everything else, right? So it's one class versus all, okay? And so for that reason, the ROC curve would not be an appropriate method for evaluation because it's a binary performance. Okay, so let me. So the ROC curve, It's a binary measure. So it measures 1 versus all. Okay, and so you for that particular problem, you would have the curve for vegetation versus everything else, and the curve for the other class would be the man-made materials versus everything else, and then you have another curve for the sand versus everything else, right? And so this would not be a good measure for evaluation of all 3 classes simultaneously, but you could still take things like, let's compute the area under each rock curve and consider the average area. Okay, but again, if this sort of defeats the purpose of using a rock curve, because if we're just averaging together the area under the curve for all classes, we're yet again using a single number to characterize the entire classifier. So we're losing the ability to distinguish performance for any individual class. Right? Okay. Okay, so for this problem, typically the best way to evaluate is using a confusion matrix, right? So the confusion matrix gives us information about the individual class performance and between 2 classes. So how is our classifier confusing each class with any other? Okay. Okay, so that's all for performance metrics. So every time we're using classifiers, in particular for a final project, so rock curves and confusion matrices are always a good method of things to include in your reports. Okay, so you have your final classifier, you show the rock curve and see that this is how my classifier is performing. Okay. Okay, any questions about this? So Andrew, yes, so rock curve is good when we're performing 1 versus all. So we're performing 1 class versus everything else. Yes. And this is particularly useful when we have imbalanced data sets, right? So when we have one class that that has a much smaller number of samples than other classes, right? So when building the rock curves, so how many thresholds we should use? So in practice, if I build a question in homework or exam, just a few, 5 or 6, right? Just to have an idea that you know how to compute it. But in practice, we're going to be using libraries to compute the rock curves for us. When we're dealing with lots of data, it just becomes infeasible to do it by hand. And so we're going to use most likely scikit-learn and PyTorch functions to compute the rock curves. Okay, any other questions about this? Okay, so so last time we were talking about the clustering. So we've ended the cluster introduction, and we've ended with k-means. And so k-means, it was a non-parametric approach to do clustering. And it's non-parametric because we don't have a function for the model, right? When you're contrasting it with, for example, a Gaussian mixture model. A Gaussian mixture model has a specific shape. It has a probabilistic model, right? It's a function to which you're going to fit the data with and find your clusters, right? K-means, it only uses a rule, right? So the way we're going to form clusters is based on distance, right? And so that's our objective function, okay? Now we're going to switch back to classification, and we're going to introduce a new classification algorithm called the K nearest neighbor. Or KNN algorithm. Okay, and KNN is also a non-parametric approach of performing classification. So it's a non-parametric approach for classification. Okay, and so, let me give an example. So suppose that we have, so again, we're dealing with classification. So we're going to have data samples and its correspondent labels, TI. And we have n such pairs, okay? And so in this example, the xi's are going to be two-dimensional. Okay, and so suppose that we only have two labels, and suppose the points look like this. For class 1, and suppose they look like this for class 2. Okay, and so the way that K nearest neighbors is going to work is so we have this training data, and now we're going to we want to classify any incoming test points. And so suppose that the test point lands right here. And so what we're going to compute is, so I like to sort of joke about K and N using the, like a dance floor type of scenario. So suppose that you go to like a dance floor and you have no idea of the choreography that people use. So what do? You just like look around and try to follow what your neighbor is doing, right? So it's just that sort of you go with what the other people are doing. So that's exactly what KNN is doing. It's going to look around at neighbors and it's going to decide the label for the test points based on the label for the neighbors. Okay, and so in particular, the K in KNN is the number of neighbors, K, that point is going to be looking around. Okay, so it finds the labels for the K neighbors. Okay, and neighbors here can be defined in many different ways. And in particular, we're going to use, we can use a distance metric, right? So a neighbor is considered a neighbor if it's close in distance to that point, right? And again, you can use many types of distances. So neighbor is such that it has the smallest distance. And distance metric can vary. But for now, let's consider the Euclidean distance, right? And for k equal to 3, maybe for this point we have that this is close and this is close, and then maybe if we had a point right here, that's going to be close to that one. Okay, so I have the point triangle has those 3 points are its neighbors. And then the way that we're going to decide the label for the point triangle is based on majority vote. That's the most common scheme for classification. Okay, so we find the k neighbors around that point, and then we decide the label based on majority votes. And so for this particular point, has 2 neighbors from C1 and 1 neighbor from C2, then we decide that the triangle belongs to class C1. Okay. Okay. And so there's many types of metrics that we could use. And that's just going to depend on the application that you want to compute. But before we go and talk about different distance metrics, yes, I was exactly going to talk about the cases when we have ties. Yes, so thank you, Nancy. So that's probably the reason why. So when we have ties, there's many different ways of approaching it. So the first one is to flip a coin, right? Just choose one at random. But that's probably not the best approach, right? Because, for example, suppose that we have the data like that and data like this, and we have a data sample that's maybe out here, or maybe maybe somewhere around here. And we're trying to find the data samples. Let me modify these red points to be more like here. And suppose that in this case, I'm using k neighbors of 4. Okay, and so I'm going to compute the 4 neighbors. So I have 1, 2. Maybe this one is closer and this one is closer. Okay, so we're going to have a tie in this case. All right, so there's 2 blue and 2 red. So one approach, again, is to flip a coin, choose it at random. But would you do that? For this case, would you think that flipping a coin would be an appropriate way of go? Why not? What is the scheme underlying that decision? That's what I'm asking. So we're likely going to just decide if we have a tie, let me use, so Andrew is saying it looks like belongs to class 2, but that's just because the neighbors for that point, the ones that are closest to it, are from class 2, right? And so in order to break a tie, we're going to decide the class with the closest neighbor. Okay, and then in this case, maybe this is the closest neighbor, and so that's going to be class 2. Okay. So Eric is making a great point. So another strategy is to always is to use an odd value for the number of neighbors. Okay, so use the odd value for k. Okay, but be aware that if we have 3 classes, even with an odd value, we can have a tie. Right? We can have a point for class 1, a point for class 2, and a point for class 3. So we have a tie still. right? But in general, we use an odd value for K, and then we use one of these two schemes to break ties. Okay. Okay, so let me see if there's any questions. I think I've answered them. And so, okay, and so now we can have different distances, right? And in here, we're just looking at Euclidean distance, but we can have many types of distances depending on the actual problem that you're dealing with. And so that's going to change your decision. Okay, so we can have, so we can also consider different distance metrics, and that decision is going to depend on the problem, on the application itself. Okay. And so let's see. Okay, so I have another question regarding K and N for you guys. So what would happen, or let me rephrase it. So is K and N sensitive to data scaling? What do you think? And by data scaling, I mean the range that each feature value takes, right? And both Tyler and Lucas are saying yes, and Eric, so that's correct, right? And the reason why, again, is because we're using distances to compute the similarity of a test point to points in the training, right? And distances are going to be heavily influenced by the scaling values that each feature takes. And so when we're using K and N and K-means or any classifier in general, it's always a good practice to scale your data, okay? To make it such that the features have a finite range from 0 to 1, for example. Okay, so the answer is yes. So we need to scale or normalize the data. Okay. And so next class, I am going to use some of the code that I have in the notes just for us to have more discussion on the behavior of KNN. Before we do that, let me know if you guys have any questions. Okay, so again, we're meeting today at 6 p.m. So I'll be sending out a Zoom link shortly in Canvas. We're going to get together to find groups for the final project. Okay, so come and join us. It's going to be fun. Okay, have a great weekend. I'll see you later today too. Take care.